contrast enhancement using phase transition information and total variation. I am Enis Çetin. I'm with the University of Illinois at Chicago. My former PhD student Serdar Çakır is with Bilkent University, Ankara, Turkey. This work is done at Bilkent University. I couldn't come to ICAST because of a visa problem, so I prepared this YouTube video clip. In this talk, we'll present a image contrast enhancement technique using Fourier phase information. So the method is a frequency domain method. The idea is to increase the weight of frequencies in which large phase variations occur in Fourier domain. Then we compute the inverse Fourier transform of the image back to the time domain. We also use total variation to smooth the final image and to estimate the thresholds that we have or some other parameters that we have. So this contrast enhancement method increases the weight of the frequencies according to their phase transitions. However, we don't modify the low frequency components because the image smooth regions of the image are determined by the low frequencies. Here is the algorithm. Given the image xmn, we calculate its Fourier transform using DFT. Image is m by n. We compute m hat by n hat by DFT. M hat is larger than m, n hat is larger than n. And as I just mentioned, we don't modify the low frequency components because the low frequency DFT components may degrade if you modify them, it may degrade the quality of the image by causing undesired artifacts on smooth regions of the image. This is the first step. We calculate the DFT. Then we have this mask, high frequency mask. It has these parameters UC, VC, which determines the low pass region of the image. Then we look at the phase of the image. Okay, phi uv is the phase. So we determine this total phase variation, or sorry, phase variation, absolute phase variation along the u direction, phase variation along the v direction, and then we check if this is greater than a threshold or not. So we will estimate the threshold using total variation by minimizing the total variation. So this threshold is not an arbitrary threshold, but it's determined by the total variation of the image. So then we have this amplification factor alpha. We use that based on the phase information or the phase transition or phase variation information. Then we smooth these values using a Gaussian type filter in the Fourier domain. Then we have the mask, final weight mask, and we use this mask to amplify XUV at only at frequencies which are above which exhibit phase transitions, and then we calculate the enhanced image. Now this enhanced image of course requires the estimation of parameters theta, phi, alpha, and u and v, uc and vc. So how do we estimate those? We estimate those by using by minimizing the total variation, U, C, V, C, theta, tau, phi, alpha, etc. These are all estimated by minimizing the total variation. Now here I have something called selective variation. So instead of uh, minimizing the total variation over the entire image, we only select busy regions of the image and carry out the optimization over the busy regions of the image, which correspond to edges and sharp regions. So we estimate the busy regions again by just looking at the changes in image pixels. Okay, so this is to reduce the goal is to reduce the computational complexity of the total variation by minimization. Here are the experimental results. So we have taken some reference images from TID 2008 image dataset, and we compared our method using the well-known Clahe methods, homomorphic filtering, and MEAM and Retinex. And we compare these images, resulting images using various uh, image quality estimation methods. And usually uh, our method produces good results compared to the other methods. Now, I have some examples here. This is the original image. This is the blurred or distorted image. And from this distorted image, we get this one, which is J. Okay, so this is the original image, distorted image, and we get this image J again. The other images are the results of various other restoration techniques. So, for example, this one, image C, is B Clahe, that also produces a very good image restoration. So this is the original image, blurred one. So in this B Clahe is again good. This is ours. And how we distort these images and so on are described in our ICASP paper. Thank you very much for listening.